All right, let us begin talking about the next topic. And this topic is going to be a pretty important one. And hopefully for a lot of you watching, it is a review topic, okay? The topic of the video is unit conversions, also called dimensional analysis, and metric prefixes. I'll give this a very high importance, about 4 to 4 stars. You may not face a problem exactly like the ones we're going to work on an exam, or definitely not your standardized exam. However, this is a very, very crucial life skill, and it's very important to you. The types of problems you might face will require you to do these types of conversions on a regular basis. Within the context of the problem, you may have to convert units at the end to express the result in units that they desire you to answer the problem in, something like that. So it's really absolutely crucial to understand this stuff. And again, hopefully you've seen it before, middle school or high school, and this is something that you are very familiar with, okay? So I always, if students are struggling with this, or I'm teaching it to the beginning students for the first time, I always start with a problem that looks like this, okay? This is a very simple unit conversion. It makes sense to us, okay? And that's why I think it's somewhat powerful to start here. What I'd like you to think about doing is converting 72 eggs to dozens of eggs, okay? The way that you would start doing that, you probably did this in your head to get the answer, is you do 72 divided by 12 to get 6, okay? Now what really did you do in terms of unit conversion? Well, you started with the unit that you had, which was the 72 eggs, and attached to it is an undesirable unit, a unit you want to convert away from. You took that, you kind of like mentally wrote it down on a piece of paper. I've got it explicitly written here, but you probably mentally did that. And then what you did is you multiplied the number that you start with the undesired units by a ratio. And that ratio is the conversion factor. I call that the conversion factor. Now the conversion factor is a fractional term. There's two values in the numerator and the denominator. But these values are physically equivalent. And what I mean by that is that 1 dozen eggs is the same as 12 eggs. They're physically equivalent. They don't have the same units, and they'll never have the same units. But whatever numbers you write in the numerator and the denominator with the associated units are physically equivalent. Like here, 1 dozen is the same as 12. Okay? So that's going to be a characteristic of the conversion factor. The numbers that you write in the numerator and the denominator won't be the same numbers. However, the number with the units in both cases will be physically equal or equivalent. Okay? Just like a dozen is equal 12 eggs. And then of course you can do the math and find 6 dozen is your answer. The reason why this works with the conversion factor is because in the denominator of our conversion factor, you always want to write the units that you're converting away from. I call that the undesirable units. Okay? So we're converting away from eggs. That's our undesirable units. That goes in the bottom of the fraction, or the denominator. The reason why that's important is when you do the math, you can cancel those units out. Alternatively, in the conversion factor, the unit that goes in the top of the fraction, or the numerator, is always the unit you want to convert towards, or to. So we want to find dozens, so that goes in the top. That's our desired unit. Okay? So desired at the top, undesired in the bottom. This undesired unit has to be the same as the unit over here, so they cancel, and they're gone. And then your answer, you're left with what you desire. Here, that's dozen. So the key characteristics of its conversion factor is it's a fraction, always going to be a fractional term, undesired units in the bottom of the fraction, the denominator, desirable units in the numerator, and the number with the unit in the numerator and the denominator have to be physically equivalent. If they're physically equivalent, it's almost like multiplying by 1. I mean, you could think of it that way, because they're physically equivalent, all right? I don't mean that in a mathematical sense, in terms of what you're going to compute on your calculator, but in fact, if these are physically equivalent, it makes sense. You're not changing things, okay? Okay, so that's how to do dimensional analysis in a nutshell. If you follow this approach, number with undesirable unit times your conversion factor, yielding your answer with desired units, it's really never going to fail you, okay? Using this conversion factor and writing it out on a piece of paper, as I've described, I think it's actually pretty crucial or important. Because sometimes students get confused. Well, do I multiply by 12? Do I divide by 12? I don't know what to do. Here it was easy because we understand a dozen's bigger than individual egg count, and that this is 6 dozen. We have a good mental picture of that, okay? But if these units aren't as familiar, it's going to be hard to figure out, well, do I multiply? Do I divide? What do I do? If you follow this approach, desired units up top, undesired on the bottom, it's never going to fail you, and you're going to know where to write what number in your fraction, because you know how to set up the physical equality. Okay, so that's an important point. Now, typically, or often, I'll say, you come across metric prefixes when you're considering this business in your class as well. And I've, in fact, reproduced a table of metric prefixes here on this slide for your use. The reason why you come across this at the time is it really has a lot to do with the conversions of units, because by using these metric prefixes we could scale by different factors of 10, either larger or smaller, to generate more convenient units than say just the base unit. So basically we don't have to write numbers in scientific notation or write a bunch of decimal zeros. Instead we can use these metric prefixes to sort of scale things to very big or very small. The numbered ones that are reproduced in this table start at 10 to the 24th with the capital Y yada, goes all the way down to 10 to the minus 24th, which is the lowercase y. You see that the big numbers, the very big numbers at the top, tend to have capital letters, and the very smaller numbers at the bottom tend to have lowercase letters. There are a little bit of some confusing points, I suppose, in here, starting about kilo. But more or less, the things that are in this table, you just kind of have to remember and memorize. The ones that I've highlighted from about 10 to the 12th, which is tera, all the way down to 10 to the minus 18th is etto. These are the ones that in chemistry you tend to use the most, okay? Things outside of that range you tend not to use quite as much. That's not to say that they're never used in science. For instance, these numbers which are really big are used a lot in, say, geosciences, like petagrams or exagrams, things like that. If you're maybe computing the mass of carbon dioxide in the atmosphere, or the amount of material that's dissolved in the world's oceans, or something like that, it's going to be a really big number, so you might use these prefixes, okay? Down here at the bottom, or we've got the really small values. These might be used if you're counting molecules or atoms at a very low level, or if you're doing really sensitive chemical analysis. You might say that you've got 10 attomoles of material or 15 zeptomoles of material, and you're doing really sensitive chemical analysis on a mass basis if you're getting down to this low level, okay? But the ones in between these two limits, you use on a reasonable basis. Now, of course, the way this works is there's a factor, a numerical factor, that's associated with each of these abbreviations or prefix. And you basically multiply this factor by the base unit to yield the prefix unit. Okay, so it's essentially a unit conversion. This conversion factor is essentially this factor over here. Okay. So let's try our hand at this just to review in case you've forgotten, or maybe you need a little bit of practice with this. Let's try some sample problems. So in the first sample problem, we see one of these types of conversions. We are to convert 117 nanometers to micrometers. Okay? So I follow my protocol. I write my number that I'm converting away from with its units, which are undesirable units. I multiply by a conversion factor. Don't know what that is yet, but I'm going to figure it out. And then I write my answer with my desired units, micrometer. Simple enough, okay? Easy stuff. Now, to get rid of my nanometer, I need to divide by that unit, so they cancel out. Likewise, my desired unit goes into the numerator, and I'm off and running on this problem. The only thing I don't know is what numbers to write here and here. But remember, they need to be physically equivalent, okay? So I look back at my table of the metric prefixes, And I find nano is right here at 10 to the minus 9. And micro is at 10 to the minus 6. So they're about 10 to the, they are 10 to the power of 3 different. A micrometer is 1,000 times bigger than a nanometer, 10 to the third bigger. Okay. So what I can do over here then is I can write that 1 micrometer is equivalent to 10 to the third nanometers, or 1,000 nanometers. The beauty of doing this is once I set up this ratio, which is physically equivalent, a micron is equal to 1,000 nanometers, I know that I have to divide this number by 1,000, and that yields 0.117 microns. Okay. If I didn't set up my conversion factor like that and I was confused, I might multiply and I get the wrong answer. Okay. So set up the units first, then do the math. It'll always help you. All right, another conversion problem. 2.1 atmospheres to pounds per square inch. That's my desired unit. I'm going to again use my conversion factor approach. Undesired units down the bottom so that they cancel. Desired units up top. Now I just use numbers to write here. Now this conversion, atmospheres to pounds per square inch, we're basically changing units, if you will. We're going to English units from more of like a sort of scientific SI type base, okay? Sometimes you got to do that. The conversion factors for such conversions are all generally really well known and reported in literature. You can look them up online or in your textbook. However, it's not something that we generally memorize. Okay, so it's probably going to be given to you on an exam. Like I'd give this to my students if I was giving this problem on an exam. And it just so happens that in 1 atmosphere, there's 14.7 pounds per square inch. And I just knew this, okay, but I'd give it to you on an exam if you needed that type of information. Okay, so you can then do the math and figure out that 2.1 atmospheres is about 30.87 pounds per square inch. And you're done. You're done with the problem. Again, the conversion factor approach helps you because you know which number goes on the top, which number goes on the bottom, atmospheres on the bottom, PSI on the top. 14.7 pounds per square inch is equivalent to 1 atmosphere. And so we know that we got everything correct. Okay, it's kind of nice when you do it this way because it will never fail you, and you can be confident that the answer that you get is in fact correct. Alright, so let's try one that's a little bit trickier. Convert 1,000 cubic centimeters to cubic meters. Alright, now this at first glance looks like a pretty simple metric unit type conversion, right? Because we got the centi and we got the base over here. So if we look back at this table, we can see that centi is 10 to the minus 2. And that's probably familiar to most of you because you know that 1 meter is equal to, 100 centimeters is equal to 1 meter. 100 centimeters is equal to 1 meter, okay? So we know that just from common experience. So if that's the case, then a lot of people draw the conclusion pretty quickly that this must be true, that 100 centimeters cubed must also equal 1 meter cubed. Now it turns out that is not correct. Okay, now to explain why, think about a cube. And I've drawn this as best I can out here in the corner. It's not a very good cube, but it's a three-dimensional object, a cube, true cube. And every edge of this cube has an identical length, and that is 1 meter. So it's 1 meter wide, 1 meter high, 1 meter deep. Okay, three-dimensional object. Now if I wanted to compute the volume of this test cube, V is equal to what? Height times width times depth, we'll say. It's from a simple geometrical argument, right? So if I wanted to do that in cubic meters, I would have 1 meter times 1 meter times 1 meter. And sure enough, the volume in this box is exactly equal to 1 cubic meter, as I've drawn it. But how many cubic centimeters is that? Okay, how many cubic centimeters is that? Let's think about that for a second. Well, I already said that I know that a meter is 100 centimeters. So I have a 100 centimeter edge length there, 100 centimeter edge length there, and a 100 centimeter edge length here. So if I'm going to compute the volume of this box, the same box in cubic centimeters, I would have to use 100 times 100 times 100 centimeters to get my units in cubic centimeters. And if I did that calculation, I would get 10 to the 6th, which is 1 million cubic centimeters. So the same box, I can express the volume as 1 cubic meter, or 1 million cubic centimeters. Alright, so in fact, the statement that we made earlier, using that just the centi prefix alone, is not correct. Okay? Now, when I look at this problem, what tips me off that I cannot just use the numbers that are in that table is the fact that I've got units raised to the 3rd power. It could be squared, it could be the 4th, 5th power, but any other power than just 1. Okay? You've got that situation where you have superscripts. You're probably going to need to generate your own conversion factor. And that's actually what we did right here. This is going to be our conversion factor that we're going to use, because these two numbers are physically equivalent with just different units. Okay? If this is a squared and a squared, you've got an area. Okay? And you've got to draw a box and figure out your conversion factor. You might be able to do it in your head if you're good, and that's just fine once you get into practice, but if you need to draw a picture, feel free, draw a picture by all means, okay? So now that we've figured out our conversion factor, I can take the exact same approach. I want to go into meters cubed. That's my desired unit. Goes up top. Centimeter cubed down below. Cancel, cancel. What do I know? Well, I know that 1 meter cubed is equal to 1 million, or 10 to the power 6th centimeter cubed. So I have to take this number and divide it by 1 million. And it looks like if I do that, I'll get 0.001 cubic meter. So that's the volume of 1,000 cubic centimeters. This is also the same as what? 1,000 milliliters, which is equivalent to 1 liter. So it turns out that's also 1 liter. There are 1,000 liters in 1 cubic meter. You can also figure that out from this analysis, okay? So what tipped me off there that I can't use just the number in the table again is we've got the cubed units, any subscripts there, you're going to have to figure out a conversion factor yourself. I like to do that if I'm confused by drawing a picture. Don't be afraid to do that and get the right answer, okay? So I hope you've enjoyed this video on dimensional analysis and metric prefixes. Please get to know these, be good at doing these types of calculations, because while you may not ask directly a question on your exam that looks anything like this, certainly not on your end of semester exam where you ever encounter a problem like this, you're likely to be asked a more complex problem that requires you to change units. And if that's the case, you really need to have mastered this skill, and you don't need to have studied something else to a large extent and be very good at that and then not be able to get the right answer just because you haven't mastered one of these relatively simple skills. Okay, so spend some time on it. If you need some help, definitely talk to your instructor or work some practice problems. Thank you.